So in the previous lesson, we found the um, integral version of Gauss's law. So this is where we had our surface integral of the electric field dot dA is equal to the total charge enclosed divided by epsilon naught. And this expression rests on the fact that we have the 1 over r squared dependence in Coulomb's law, and that cancels out. Now, we can also write this in a differential form. The integral form is very useful for determining point, line, and surface charges quite easily. But if we look at the divergence theorem, and we can write our surface integral of E dot dA, and this is equal to the volume integral of the divergence in the electric field, d tau. Okay, d tau is our infinitesimal volume element. Now we can write this total charge enclosed as the volume integral of our charge density rho. Now this here is going to allow us to express our right hand side of the divergence theorem in terms of rho and epsilon naught. So we have our volume integral of the divergence of the electric field, d tau, equal to the volume integral of rho over epsilon naught d tau. Now, since this is going to hold for any volume, what it means is the integrands for both sides must be equal. So now what we get is the divergence in E is equal to rho over epsilon naught. Okay, now this is the differential version of Gauss's law. You can see it's quite neat. What we want to do is do a quick problem. We're going to suppose that we have some electric field in some region, and it's given by E is equal to K R cubed R hat. Okay, so this is what we're talking about here. It may not show up so well in the video. And K is some constant. Okay, this is in spherical coordinates. The first thing we want to do is to find the charge density rho. Okay, so what we can do is we can write rho in terms of epsilon naught by the divergence of E, our electric field. And I've given up here the divergence of the electric field in spherical coordinates. So here we have rho is equal to epsilon naught by 1 over r squared, then the derivative with respect to r of r squared by kr cubed. Okay. So we take the derivative of this, we're going to get 5k r to the 4. So what we have here is epsilon naught by 1 over r squared by 5k r to the 4. And so we get an answer of our charge density rho is equal to 5 epsilon naught k r squared. Okay, so here's a charge density. In the other part of the question, what we want to do is to determine the total charge contained in a sphere of radius r centered at the origin. Okay, so what do we have here? Well, we just write down Gauss's law, so we have our surface integral of E dot dA is going to be equal to total charge enclosed over epsilon naught. So dA will be equal to r squared sine theta d theta d phi in the r hat direction. Okay, so now what we get here is we can write our integral as integral between 0 and 2 pi for phi, between 0 and pi. The electric field is given by k r cubed. Okay, so it's given by k r cubed r hat. K r cubed r hat dot r squared sine theta d theta d phi r hat. Okay, so the integral will work out to be 4 pi. Okay, so now we have the total charge enclosed over epsilon naught will be equal to 4 pi r to the power 5. So we've got 4 pi k r to the power 5 Okay, so this gives us our total charge enclosed. So we can also do it another way. We can also determine the total charge enclosed by looking at our volume integral. Okay, so we can have Q close equal to our volume integral of rho d tau. Rho here, we just calculated before, is given by 5 epsilon naught kr squared of 5 epsilon naught kr squared and our volume integral over the sphere is given by r squared sine theta dr d theta d phi, and we have our integrals between 0 and r, 0 and pi, and 0 and 2 pi. So what we get here, we're going to have r to the power 4 to do the r integral first, and we're going to be left with r to the 5 divided by 5, so the 5s are going to cancel. If we do the integral with respect to theta and phi, we're going to get 4 pi. So what we get here is 4 pi epsilon naught by k r to the 5. Okay, so you see that we can get the same answer by doing it two different ways.